Good morning to everyone. My name is Mouhamed Gueye, and I'm geologist for Osisko Mining in Canada. So firstly, I will thanks all the members to participate to this forum, and thank you we have good presentation today. I'm really glad to be here with you. So my subject today will be focused on the application of the 3D modeling to highlight karstic cavities in the chest forest. Thies is a small town in Senegal, and we'll see it in the presentation. So it's the application of the 3D modeling to highlight these karstic cavities in this chest forest, in support of planning soil consolidation, work by grout injection on cement work or cement factory. So we will see together the perspective on the influence of the climatic factors. So this presentation will be addressed like this. Firstly, we will see the geographic and the geological context of the field. And in the chapter 2, we'll see the methodology from the data collection to the recommendation made for the fields. So in the chapter 3, we will see the 3D modeling of car lens form or edifices. And finally, we will see together the perspective on the influence of climatic factors. So in summary, the construction of cement work in karst environments require careful consideration of the issues related to differential settlement. So in the chess fields, you have the biggest problem of settlements in the batching plant of the cement factory. So the injection of grout is a mix of water, cement, and sometimes sandstone. So it's a geotechnical solution applied to this. So we have two major problem with this geotechnical solution. The first is we don't have a visual support, a good visual support. So it's a solution which is threat in this subject. So the other problem is the efficient control in climatic process. So when we talk about climate, we don't have a very good control in this fact. So we'll see together this both major problem and how we try to solve it. So the geographic and the geological context. So the field of chess is located here in the western part of Africa. So we are in a small country in the western part of Africa, which is called Senegal. So it's geologically it's a Mesocyanozoic basin, so which is filled by essentially limestone units. So the thickness of this limestone unit are near to 7,000 meters. So for the hydrogeology, when we talk about karstic edifices, we need to understand the configuration of this karstic and the aquifer unit. So we have two biggest units of aquifer in the Senegal, which are connected. So we have the deep Paleocene aquifer, which is constituted by sandstone and limestone. And we have the superficial Paleocene. So it's the biggest aquifer which is near our field. It's a zoogenic limestone, and we have an pre-Eocene classification here. So for the geology, in the structural, we have very important unit. So it's very important to understand the structural in the field. So it's help us to know how about the structural configuration of our aquifer. So we can have normal fault and major fault, so and moderate shear zone too. So for the geology, we can differentiate the undifferentiated gas group, which is dating from the Campano Maastrichtian, and another which is called the Poponian Formation, which is Paleocene shell and limestone mix, and sometimes can have sandstone, very thick bed of sandstone. So let's see the methodology. How about the drilling program? So our field is close to an international airport. It's the biggest international airport of Senegal. So we are in a classic forest. So all the problem which is found here will be applied to the AIBD, the international airport. So we have the two biggest cement factory in West Africa is the Sahel Cement. Sahel Cement is just located in the northern part, and we can have the Dangote Cement, which is just in south. So we think that there is an contribution to the acidification of rain in this zone, and it's very important to control it, to have an efficient control of the classification. So for the drilling program, we have 31 drill holes which are planned in the field. So the biggest objective of this campaign of drill holes is to have a description and correct and a very important description of the lithological units. So it's help us to pinpointing the classified horizon in the fields. And with this database of drill hole, we can do it will be the database for the block model. So with these 31 drill holes, we do what we call an stratigraphic correlation. It will help us to know and to have a broad idea on the thickness of different geological units. And here we have the clay formation and the calcified unit, which is a limestone. So we interpret an host and graben between the S05 drill and the S14 drill holes. So here we can have an visual appreciation of the clay unit. So we can have lateritic concretion in the clay unit. So it's very important geotechnically to know how it can affect our zone. So for the calcified limestone, we can see we can have an visual appreciation too of the classification. Here we can have a metric gaps. So the rocks are very broken and it's a very big program geotechnically. So we interpret and progradational classification until the depth. And the evidence of calcified horizon are highlights in drill program with an acceleration and drop in the drill holes, the drilling tools. So here again, we can see the nature of gaps in the geological limestone. And so another kind of test that we done is what we call an pressometric test. It's another geotechnical test, which is very important. So the first is the pressometric test. Here we can have the device and a table which permits us to know how about the pressometric modulus and the reservoir of gas with the tubes, and here and son with which is in contact with the geological unit. So we can share some important modulus such as the pressure limit and the compressibility modulus. So this modulus is very important because it will let us know how about the compressibility of the formation. And this kind of data we treat after the pressometric in situ test is this kind of diagram. Here we can appreciate it, the evolution of this report. It's a very important report, EM out of PI. So when we see that the diagram is decreasing, we can know that we are punctual cars here. So another important diagram, the EM out of PI, we can appreciate to the water loss in each drill hole. So it's very important to do recommendation after this program. So we'll see the 3D modeling of cast line landforms and edifices. So for doing this modelization, we use an geological software which is called SURPAC that a large number of geologists know. So SURPAC is an geological modeling software which is used to with resource and resource estimation. We use it as well for design and planning mining and optimizing mining parameter. We use to designing mining infrastructure, but it's less common. So here we have displayed the 31 drill holes of the zone of studies. And after this, we display what we call the primary block model. So it's a global block model that uh, can let us know how about the surface and the vertical extension of our model. So after this, we display and modelize each hanging wall and footwall of each formation. Here we have the clay unit, and here we have the limestone unit. So, and when we superpose the both unit, we can have a block model. And with the RQD of each rock of each drill hole, so it's very important to know how the correlation will be matched and to use the AI to display the classified units. So when we use the RQD parameter, we can display this kind of zone P1, P2, 3, and L4. So in red, we can see that it's the most calcified area, and we need to stabilize this zone in priority to set up our batching plan and our cement factory. So we've seen that this zone P1 is the most pronounced calcification zone. And after that, we have the P2 and P3 and then P4. Here we don't have sufficient drill holes to interpret, but it's very important to focus the injection in these two areas. So the final model, we interpret an west to east retrogradational calcification. And we've seen that it's a frequent rise of the water table in zone P1 and as well P2. So it can due to a differential height of the pressure metric level. So for the volume estimation, we use the inverse distance because it's more representative. The total volume of limestone is 8 million cubic meter, and the volume of cavity 56. You can have 56 hundred, 56. Yes. And for the injection, we use what we call a batching plan, a moderate batching plan. We do a mix of sandstone and cement and water to fill each gap on the fields. So it's a very important and a very aggressive geotechnical method, and it may be very, very, very important parameter to control here. So how about the climatic factors and their influences and contribution? So when we call about injection, there is a very important parameter such as physical or chemical to control. Here we can have, it's true, we can have an efficient long and medium term stability for the setup, and the cementation help us to limit the H2CO3 production. So the H2CO3 production is an acid. So when the CO2 of atmosphere and the soil, the topsoil, react with the H2O coming from the rain, it's product an acid, and this acid H2CO2 will be react with CaCO3, which is in limestone units. So when we fill these fractures, we can limit this production of H2CO3, and as well we can limit the calcification. It's the ID which will be that we applied here. So another parameter is the local rain acidification due to the presence of another cement factory in near the zone. So can have an exponential production of H2CO3. That here we can have an good control of this. It's a very big problem here, and we know that classification is an very slow process which can take several years. So let's see the indirect influence of the injection process. As we say, it's an very aggressive geotechnical model solution. So punctually near the area, we can have a modification of the permeability and porosity of limestone. So when we fill the gaps, it's clear that we will have a modification of the permeability. And as well, this kind of factor will be affect the water cycle and the recharge of underground aquifers. So it's a very big problem when we decided to apply this solution, this geotechnical solution. So we will have problem of water near the site, and we know that in Africa water is essential. So we can have two local difficulties in water availability, as we say, for the population as well and the vegetation. So another big problem is the groundwater quality, because of when we fill this kind of cracks and fractures, we will have a decrease of natural filtration and purification of the karstic landform. So it's an important properties that we will lose until the year. So one of the biggest problem is the increase of the residence time of water in aquifer. So we need to understand that when water is have a big time of residence, it will affect the groundwater quality. So we'll have a biggest problem of geochemistry of the water. So in conclusion, we need to focus on three major points to apply this geotechnical solution. Firstly, we need to focus on the protection of the water quality. So it's very important. We are in Africa. We need to have an very efficient water production and quality. So we can use to an integrate approach with the population which are near the site to explain them how we can affect them and let they know what are the solutions that we have to apply. And we can invest too in the research on the dynamics of climatic parameter, because we need to have an better understanding on how climates can affect in long term in our field. So it was the very important point that I wanted to share with you. So my presentation is end. So if you have question, you can let us know. Any question?